Hello, welcome back. We are spending 2 lectures discussing NP-complete. In the first lecture, we learned the Cook-Levin theorem, the definition of NP-complete. We have seen some NP-complete problems, for instance, set and k-click, and we showed how to prove a new problem to be NP-complete. In this lecture, we will see one more NP-complete problem. Recall the definition of NP-complete. A problem X is NP-complete if it satisfied two conditions. First, X must be in the class NP, meaning X can be verified in polynomial time. Second, any problem in NP can reduce to X, meaning X is a hardest problem in the class NP. In order to prove a new problem to be NP-complete, it is easy to first show that this problem is in NP. For the second condition, instead of proving any problem y reduces to x, we only need to show that there is at least one known NP-complete problem y that reduces to x. In other words, we use a known NP-complete problem to stand in for all the other problems in NP. This idea shows the meaning of complete. All NP-complete problems have the same difficulty level. All of them are the hardest problems in the class NP. We can use any proven NP-complete problem to prove a new one. This is like the idea of seeing the superheroes all in the same club. If anyone wants to join them, one only needs to defeat one of them. So proving problems are NP-complete can get easier and easier as we have identified more and more NP-complete problems. Set, CNF set, k-click, and Hamiltonian cycle are all NP-complete. There are hundreds of discovered NP-complete problems. If you are interested, the Wikipedia page provides a good starting point to read about this topic. Note that these problems do have algorithmic solutions. They're just too time-consuming and generally regarded as intractable using the computers we have. Small instances of these problems can still be solved using computers, and approximation solutions can be provided for some large problem instances. Now we show the proof of another NP-complete problem, the k-vertex cover problem. We will reduce the k-click problem to this one and show how a reduction can be constructed between two problems that are in the same domain. The word cover means that a subset of vertices S cover all the edges in the graph G. In this example here, we know that vertex Z and W is a two-vertex cover because they are attached to every single edge in this graph. An example application of the k-vertex problem is to test for link failures in a communication network. K-vertex cover gives us a set of k-nodes that are capable of testing every link in the network by, for instance, pinging the nodes at the other end. The optimization version vertex cover problem is to find a vertex cover of minimum size in a given graph. Here, k-vertex cover is the decision version for it. Thus, a graph G contains a k-vertex cover. The naive brute force algorithm for this problem would be exhaustively enumerate all subsets of k vertices and see if any of them covers all the edges in E. Say there are n vertices in this graph G, so we need to enumerate n choose k subsets. This is factorial and not polynomial time. Do we have a polynomial time algorithm? We don't know yet. Now it is established that this seems to be a very hard problem. Next, let's prove that this problem is in fact NP-complete. There are two steps to prove the k-vertex cover is NP-complete. First, we show that k-vertex cover is in NP. Given a guessed solution, a subset of k vertices, we can go through all the edges in the graph and see if they are covered in the vertex subset. This can be done in polynomial time. Second step, we will show that a known NP-complete problem, k-click, reduces to k-vertex cover. We transform each input instance of k-click to an input instance of k-vertex and show that such a transformation is answer preserving. That is, if the answer of k-vertex cover is yes, then the answer to k-click is also yes, and vice versa. We need one more definition before we talk about the transformation, the complement of a graph. The graph G complement has the same set of vertices as G and a complement set of edges, meaning if two vertices are connected in G, then they are not connected in G complement, and vice versa. Given G, we can easily construct G complement in polynomial time. Next, we will show how we can phrase a vertex cover problem on G complement that is answer preserving with the original k-click problem on G. We need to show that graph G has a k-click if and only if G complement has a vertex cover of size V's cardinality minus k. Is this transformation in polynomial time? Yes, constructing the complement of a graph is in polynomial time. Is this transformation answer preserving? Let's prove this by showing the two directions. Direction 1, when G has a k-click, can we show that G complement has a vertex cover? You can pause and read through the proof process. Here we're going to show you an example. This is the graph G. We have 5 vertices. And we have edges like this. And then we can construct the G complement accordingly. G has a 3-click. So these are vertex 1, 2, and 3. The rest of the vertices are then 4 and 5. We also have n equals 5 for this example. For any of the edges in G complement, they cannot be in G by definition. So that means for those 4 edges, at least one endpoint does not belong to the click 1, 2, 3. So that means all of those 4 edges have one endpoint in the set for 5. And that's the definition of vertex cover. So we know G complement has a 2 vertex cover, vertex 4 and vertex 5. So what about the other direction? We know n is 5 here. G complement has a 2 vertex cover. These are node 4 and node 5. So we know these 2 vertices are attached to all the edges in the graph. So in G, for the vertices that are not in the cover of G complement, node 1, node 2, node 3, there must be an edge connecting all the pairwise of these 3 nodes. Because if there isn't an edge in G here, there will be an edge in G complement. Then one of these 2 nodes, either 1 or 2, will have to be in the cover. But that's not the case. So by contradiction, we know that all the nodes that are not in the cover, nodes 1, 2, 3, they have to be connected pairwise directly by edges in G. So that's the definition of k-click. So we know nodes 1, 2, and 3 form a click. Now we have proof that k-vertex cover problem is NP-complete. You may have noticed that since both the k-vertex cover and the k-click problem are both graph problems, the transformation seems more intuitive and straightforward, especially comparing with transforming CNF set to K-click that we saw in the previous lecture. I hope now you have a good grasp of the class P, class NP, and NP complete. Finally, let's see the relationship among these three classes. The class NP includes all problems that can be verified in polynomial time, and P is the set of problems that can be solved in polynomial time. NP complete is the class of the most difficult problems in NP. All of the NP complete problems can reduce to each other. This diagram is how almost all computer scientists view the relationships among P, NP, and NP complete. Both P and NP complete are wholly contained within NP, and P does not overlap with NP complete. I hope this week's lectures help you get a solid understanding of distinguishing between easy and hard problems using current computers we have. However, you can imagine that with quantum computing, for instance, being advanced in the future, polynomial time might not still be the boundary defining hard problems. There is much exciting research, and you may be the one of the computer scientists exploring that front. Okay, that'll be all for this lecture for this week and for our first topic, complexity. There are some truly beautiful and fascinating theoretical computer science work here. I hope you enjoyed it and found it useful. I will see you next week.